Now get out your protractors, rulers, and grid paper. Draw the following problems and solve them using the trigonometry method discussed previously. You can check your answers when finished. Vectors are a great way to describe forces acting on an object, including both the direction and the magnitude of the forces. Vectors are also good for describing kinematic conditions such as displacement, velocity, and acceleration. Each of these will be discussed in future lessons. You should be able to do the vector capstone problems built into the course now, but if you are still having trouble, you should read on. Additionally, if you would like a more hands-on approach, you could go to this website and work on this virtual laboratory. It shows an example of a classic laboratory physics setup which we have created in the following slides as data tables and graphs. It is not a free service, but there is a 60-day free trial period if you would like to explore the activity. The first three exercises in this exploration use graphical representation to remind us that force addition is done using the x and y components independently. Refer to the previous pages if you need to review vector addition. For each force, determine the x and y components by counting the number of squares. Include the appropriate plus and minus signs. Then add the total number of x and y squares from all the forces and draw the net force vector on your graph. You can imagine that this is a top view of the force table shown in the picture. Each of these arrows represent a force pulling the center ring of the table with various strengths or magnitudes in various directions. The concept is to add these forces into a single net force. Finish the problem by summing the x and y columns. When you count the number of blocks in the x and y direction, you are separating the vectors into components. This will be the same process that you will have to do mathematically using basic trigonometric functions. The x component will be found using the cosine, while the y component will be found using the sine function.
Five minus 2 is 1. 2 and negative 3, negative 4.5, 2. 2, 6, 1.5, 5, 4, 1.
Count the blocks in the x direction. Count the blocks in the y direction. Sum these columns up and you have the net force in the x and y directions. On the following slide you will see how these sums can be used to find a resultant vector force. Recall that vectors need both a magnitude and a direction.
1, 2, 3. 0. 1, 2, 3, 4, negative direction. 1, 2, 3, 4.5, positive direction. 1, 2, negative direction. 1, 2, 3, 4, negative direction. 1, 2, 3, 4, positive direction. 1, 2, negative direction. Sum. 4 and 4 is 0. Differences 1. 4 and a half, that's positive 5, negative 1 and a half. See if we're right.
The next two exercises review the addition of forces using the mathematical procedure of vector addition. Again, refer to the vectors lecture if you need to review this material. The procedure for all of these problems is the following.
40 cosine 45 gives you the x component. 40 sine of 45 gives you the y component. 0 in the x, 30 in the y. Vector 3, negative 50, cosine 30, and negative 50 sine 30 gives you the following answers. Add 28.30 and negative 43.3 to get 15. Add 28, 30, 25 to get 33.3. Place these two on the graph. Negative 15, up 33. Pythagorean theorem allows you to get force net, and the angle is measured 66 degrees from the horizon.
Work the following problems by using common trigonometry relationships as demonstrated on the previous slides.
30 sine, 30 cosine, 45 sine, cosine, no x direction, all y direction. Add them up. Approximately 71. Don't forget to make this one a negative. Don't forget to make this one a negative. So 1556, approximately negative 40. Approximately 44. So negative 40 will be back this way. 44 will be up this way. And you see the resultant. We could measure this angle. Notice the correct answers are listed beside the red blocks.
If you can do problems like this mathematically, you should be able to apply the free body diagram concept to any force problems, aka static problems that are presented in this course. After reading your textbook's description of drawing free body diagrams, you should be able to draw diagrams for the following examples, and then follow the process described to do analysis on these using Newton's second law. For each of the following situations, complete the following.
Notice you have a thrust in the x direction, a lift in the y direction, drag in the negative direction, and weight down. In example 2, your vector is at 30 degrees, you have a vector up, you have a vector drag backwards, and you have a weight vector down. These problems should be completed during the course.
The main ideas between the theories of Newton's first, second, and third laws have been introduced. Now it is time to give an overview of these laws. Newton's first law summarizes this by saying an object at rest will remain at rest, and an object in motion with constant velocity will remain in motion with constant velocity, unless the object is acted on by a net external force. The study of objects with zero acceleration is called statics. Whenever the object being studied has a zero acceleration, velocity is constant, then Newton's second law becomes: the object is said to be in equilibrium under these conditions. An object in equilibrium can be at rest with a velocity of zero, or it can be moving with a constant velocity. Remember that a net force of zero is required for constant velocity. When working a word problem or analyzing a situation in the real world, there are prescribed steps that need to be followed. These steps have been discussed previously and are listed here in order. Following this procedure will result in a better understanding of statics and dynamics. This type of complete presentation reflects to others that you are knowledgeable and competent. Here is a classic example of a traffic light hanging from two cables. What is the weight of the traffic signal that is causing this cable to bend at the following angles? The tension in the cables is given as 60 newtons. Here's how we solve this problem. To find the weight of the traffic signal, we would need to draw a physics representation, a free body diagram. But first, you should look at the real-world representation and draw arrows in the direction of the forces that are acting on the traffic light. You are now looking at a simplified model of the physics representation picture. This is the free body physics representation. Assume this is what the textbook describes as a free body diagram. This is the mathematical representation and solution to the problem. Remember the conditions for equilibrium. Newton's second law states that the sum of the forces in both the x and y directions need to be balanced if this hanging object is at static equilibrium. Therefore, you can break the tensions into both x and y components, as previously done in trig problems, and you can demonstrate that the upward and downward y components are equal to 0, and the left and right components in the x direction are also equal to 0. Hence, this final mathematical representation shows the static nature of the hanging traffic light. On your own, solve this problem using the example on the previous page. Draw a free body diagram showing the forces on the skier. These would include the pull from the cable, the force of gravity, i.e. the weight of the skier, the normal force, and then some frictional dragging force from the water. After you draw the forces on your diagram, think about this question. What does constant velocity mean? All the forces on the object should be equal. The skier is in dynamic equilibrium, which means that the forces are balanced and the velocity would be non-accelerated. The velocity would be constant. Therefore, the frictional force has to be equal to the constant horizontal force of 300 newtons, so that the skier is in equilibrium and hence has a constant velocity. So the answer is, the frictional force must be equal to the pulling force, 300 newtons. Follow the three-step outline process that eventually leads you to fill in this chart. On your own, follow the three-step outline process that eventually leads you to fill in this chart. This lesson is complete, and you should now be able to draw free body diagrams. Understand that balanced forces imply constant velocity motion, and that unbalanced forces imply an accelerated motion. Good luck with drawing your free body diagrams and analysis of motion types and equilibrium conditions while doing your capstone exercises and any additional homework problems you see necessary. In this lesson, you cover the following objectives.